performing basic matrix operations. So in this section, we are covering a ton of different topics, yet they all fall under basic matrix operations. So my plan is to go through one or two from each section with you guys, leaving, one or two for us to go over during class, depending on the sections that you guys would like to see more of. So the basic groundwork here is we have matrices. A matrix is a rectangular arrangement of numbers in rows and columns. Okay, so we call the rows as our M for rows and N for columns. So you guys will commonly see matrices referred as M times N, which would just be rows times columns. So we call the numbers in a matrix our elements. Okay, so these are the elements of a matrix. We name matrices as a capital letter. We have matrix A here, which is 3 rows by 2 columns. So we say that two matrices are equal when they have the same dimensions and the elements in the corresponding positions are the same. Okay, so we'll look a little bit at what it means for a matrix to be equal to. As with 1 through 3 here, we are just solving these matrices for the missing variables. Okay, so let's dive into number 1 here. Okay, so when we're looking at these matrices, these are 2 by 2, 2 rows by 2 columns. Okay, so we can solve for the missing rows because we know that the corresponding position have the same dimension to the elements in the corresponding position. So our 2 and T are corresponding elements. Same goes with 3 and H, M and -4, A and 34. So if we're solving for our missing variables, we can just correlate them to its corresponding element. So if we're solving for M, we know that M equals -4, right there. A would equal 34, T equals 2, and H equals 3. Okay, that is all we have to do to solve for our missing variables. Although we will get certain times, like in number 2, where we have variables in our corresponding elements here. Okay, so if they're equal, we still know that these are equal statements. Like in our top position here, we have 5x, which is equal to y. And we know that 5x plus 4y is equal to 10. So right here, you'll notice we have a system of equations. Okay, since we have y equals with no coefficient, why don't we use substitution here? So let's substitute 5x in for y. So with our next step, we can take 5x plus 4 times y, which we know is 5x, which equals 10. Let's go ahead and solve the system. 5x plus 4 times 5y, which would be 5x, equals 10. So 5x plus 20x equals 25x, which equals 10, which if we were to divide 25 from both sides, we would get x equals 10 over 25, which we can simplify as 2/5. Let me get that text box out of the way. Okay, there we go. Okay, so that's our answer for x. Now we can solve this for y with substitution. We have 5 times x, which is 2/5, equals y. So let's go ahead and multiply. 5 times 2, which is 10, over 5, which would ultimately equal 2 equals y. Okay, so at this point, we have solved for both of our missing variables using our linear systems operations. Okay, the next section here, we are adding and subtracting matrices. So as you can see in the column below, you find your corresponding elements and which in the same positions, and you just add them together. So let's just look at our first couple, or let's just look at examples 4 and 6 here. So our corresponding elements would be elements like 2 and -6, and so on and so forth. So let's go ahead and add them. We have 2 plus -6, which is -4, -1 plus 9, which is 8, 3 plus 7, which is 10, 7 plus -11, which would be -4, 14 plus -8, which is 6, 9 plus 17, which is 26. And when you're adding matrices, your solution will be a matrix. Okay, you can do that same exact steps with subtraction, but instead of adding, you would obviously subtract. But let's take a look at number 6. Obviously, these two matrices look very different from each other. This one right here, you have 1 row and 2 columns. And in this matrix, you have 2 rows, but only 1 column. So these matrices have different dimensions. So it is not possible to add or subtract them. So for your solution, you were right, not possible. And then if you need an explanation, because matrices have different dimensions. Okay, the matrices must have the same dimensions in order to add or subtract. All right, we'll save number 5 for class, but give it a try on your own. Looking at page number 2 here, we have scalar multiplication. So we'll just do example 7 here. So a scalar multiplication, you are essentially multiplying your scalar by every element inside the matrix. So you would take -3 times 2, -3 times -16, so on and so forth. So this would equal, let's see, we have our matrix, we would have -6, 48, -3, -3 times -9, 27, -3 times 5, -15, -3 times 0, which is 0, -3 times 4, which is -12, -3 times 22 is -66, -3 times -7, which is 21. And there we go. That is our scalar multiplication. Do that same process with number 8 if you would like. We can go ahead and go through that in class tomorrow. Okay. What is element A, 3, and 2? So what this means is this is asking us what element is in the position 3, 2. So 3, 2 means that it would be in row 3 and column 2. So let's find row 3, 1, 2, 3, and column 2, 1, 2. Right there. We have -66 in that position. All right. Hopefully, scalar multiplication makes sense. Please make sure to ask questions in class if you have them. So, in our next section here, we need to find each of our missing variables. So we have scalar multiplication here equals another matrix. They have the same dimensions, so we should be good to go. So let's start by multiplying our scalar multiplication. So we have 4 times x, just gives us 4x, 4 times y minus 1. Remember, when you have multiple elements, you would have to distribute. That'd be 4y minus 4, 4 times 3, which is 12, 4 times z, which is 4z. And that equals our other matrix, 28, 6z, x plus y. Okay? So now let's go ahead and solve for our variables. Okay, we have 3 different variables here. So let's go ahead and solve using our corresponding elements. So we have 4x and 20. Let's set them equal to each other. 4x equals 20. We can go ahead and solve for x here. Divide both sides by 4. We'll get x equals 5. Right there. Let's do the same with z. Z. In our bottom left hand here, we have 6z equals 12. So we can go ahead and set that up in a very similar way. 12 equals 6z. Go ahead and solve for z. Divide both sides by 6, which will give us z equals 2. Okay? Our final variable to solve for would be y. I do believe that our easiest element to solve for y would be this one in row 1, column 2. So let's take 4y minus 4 equals 8. Go ahead and add your 4. That'll give us 4y equals 12, which, if we were to divide both sides by 4, we would get y equals 3. Here we go. We have solved for all 3 of our missing variables. Okay, go ahead and give number 10 a try on your own. We can save that one for class as well. And the final thing we need to talk about is that matrices are also used to represent points and polygons. So the ordered pair xy can be represented by this column matrix x over y. Okay? Same with if we had a polygon like triangle ABC. With these vertices, you will see the vertices are represented the same way. We have x over y, x over y, x over y, right? You are representing each of these vertices ordered pairs in matrix form. So by representing ordered pairs as a matrix, it allows us to perform transformations easier, especially dilation, which is essentially just scalar multiplication. Okay, so let's determine the new coordinates for ABC if it was dilated by a factor of 2, so it was double. Okay, so we know ABC's vertices are represented by this matrix, so let's start there. We have 3, negative 2, 1, 2, 1, negative 4. Okay, if our dilation factor is 2, we need to use a scalar multiplication of 2. Okay, we can definitely figure this out. Just multiply 2 to each of our elements. 2 times 3 gives us 6. 2 times negative 2 gives us negative 4. 2 times 1 gives us 2. 2 times 2 gives us 4. 2 times 1 gives us 2. And 2 times negative 4 gives us negative 8. Okay? But this right here, this isn't coordinates. We want to write our coordinates as ordered pairs. So when we are doing a transformation of a polygon, we write each of our vertices as a prime, or our vertice prime. B prime, C prime, so on and so forth. Okay, let's go back just in case we need the space here. So A prime, remember we have X over Y, would be 6 over and 4. 6 is our X, 4 is our Y. B prime would be our second row, or second column, sorry, negative 4 and 2. And finally, C prime would be our third column, 2 and negative 8. Okay, these right here are the new coordinates of our transformed polygon. All right. Final question here. We have one more geometric translation. Okay. So we can translate geometrically by adding matrices. Okay, so we have this quadrilateral, QUAD. Okay, these are our coordinates right here. We are going to move these coordinates up 2 units to the right and 1 unit down. Okay, so let's start by writing our vertices as a matrix. So remember, we write X over Y. So we have negative 2 over negative 3. Let's go on to U. We would have negative 1 over 2. A, we would have 3 over 4. And D, we would have 1 over negative 2. Right there. That is our matrix to represent our quadrilateral quad. Okay, if we want to move this 3 units to the right and 1 unit down, we would have to add 3 to our x values. That would move it 3 to the right. So we would add 3 to each of our x values, which is on top. And then if we want to translate this quadrilateral 1 unit down, we would need to subtract 1 of our y values. Okay, from here, this is basic matrix addition. So add each of our corresponding elements, like negative 2 and 3, negative 1 and 3, so on and so forth. So let's go ahead and add. Negative 3 or negative 2 plus 3 would give us 1. Negative 1 plus 3 would give us 2. 3 plus 3, 6. 1 plus 3 gives us 4. Now on to our y coordinates. Negative 3 plus negative 1, negative 4. 2 plus negative 1 gives us 1. 4 plus negative 1 gives us 3. Negative 2 plus negative 1 gives us negative 3. Once again, we can't just leave our vertices as a matrix. So let's write them as we did for our triangle above. So we have Q prime equals our first column here. Remember, X and then Y. U prime is our second column, which would be 2 and 1. A prime is our third column, which would be 6 and 3. Then finally, D prime is our fourth column, which is 4 and negative 3. Okay, this right here is our geometric application for matrices. Okay, we will have much more practice in class the upcoming days on basic matrix operations. We'll go through those couple that we skipped, trying to make the video as short as possible. Please give them a try on your own and then bring questions to class. Thanks for watching.